Our next paper is Wave-Guided Field-Aligned Volume Filling Curves by Giovanni Cocco and Javier Chermain.
Hello, everyone. Today we will discuss volume filling curve, continuous curve that traverses and fills an entire volume without self-intersecting. The volume is assumed provide as input and must consist of a single connected component. And this requirement ensures that the curve can continuously pass throughout the entire volume without becoming disconnected. In particular, we focus on field-aligned curves, meaning that the curve tangent should align with a given tangent field. These fields exhibit a twofold rotational symmetry, so directions are considered equivalent up to a sign change. In other words, it can be viewed as a line field rather than a vector field. To define the volume filling objective, we require the distance between neighboring parallel segments of the curve to remain close to a prescribed target value denoted by tau, and this target spacing controls the density of the curve within the volume and help ensure a uniform filling of the domain. To summarize the problem, we take as input a volume, a two rosy tangent field, and a target spacing, and produce a field-aligned volume filling curve represented as a polyline. Generating field-aligned volume filling curve is still a challenging problem, as the curve must simultaneously satisfy the alignment objective imposed by the underlying line field, while also achieving the desired volume filling behavior. Repulsive curves appear to be the only method that achieves both of these objectives using a curve-growing approach. As this general framework can be applied to a wide range of applications, however, it suffers from long computation times and often struggles with local minima when applied for field alignment. More recently, Noam and colleagues proposed a new curve-growing approach that significantly improves computational efficiency. However, their framework does not include field alignment objective, limiting its applicability when alignment with a prescribed line field is required. And before diving in our method, I want to give a quick intuition of why generating field-aligned space filling curve by growing is challenging. In this simple example, we will consider a 2D domain and a constant tangent field in the horizontal direction. And on the right, we show what the target result could look like. Curve growing method iteratively extends a curve by following the gradient of an objective function. This objective function will contain two terms, a space filling energy and a field alignment one. The field alignment term encourages the curve to grow horizontally. However, this objective alone will not be sufficient to fill the domain. The space filling term instead encourages the curve to expand in all directions to cover the space, and it will ignore the tangent field. The main challenge is these objectives in most cases are competing, and balancing field alignment and space filling objective while avoiding local minima is extremely difficult and remains an open challenge in the design of curve growing methods. To address this challenge, we rely on a different approach. Instead of directly balancing competing objectives during curve growth, our method is designed to better accommodate for both field alignment and volume filling requirements by using a constructive approach. We first generate two wavefronts that are mutually orthogonal and orthogonal to the tangent field. Then we compute their intersection, which will yield a set of closed curves. And finally, the set of closed curves is stitched together into a single field-aligned volume filling curve. And we start by describing the wavefront generation. We seek to generate two wavefronts that are orthogonal to each other and to the target tangent field. To guide this wavefront throughout the volume, we first generate a frame field in which the normal direction guides the first wavefront and the bitangent direction guides the second. And before diving into more details, I will briefly present the discretization of our domain. The input solid is encoded as an STF on a dense voxel grid, which also stores all other fields. A fine voxel size of tau over 4 is used to ensure sufficient resolution to capture the required geometric details. Okay, I will now begin by describing how the frame field is generated from the tangent field. So if we consider the geometric setup, the axis directions are chosen to be mutually orthogonal, forming a local frame, and all directions are too rosy, since the wavefront generation is invariant to a direction or its opposite, as I will discuss later. The tangent direction is again given as input, and the goal is to complete into a consistent orthonormal frame field by determining the remaining normal and bitangent direction in a way that preserves orthogonality. And since the tangent is already given, specifying the normal is sufficient to fully determine the frame, as the bitangent can then be obtained as the cross product of the tangent and the normal, completing the orthonormal basis. Therefore, we generate the frame field by optimizing for a smooth two rosy normal field under the constraints that it remains orthogonal to the given tangent field. This smoothness objective is mostly motivated by the observation that wavefront generation is easier where driven by more smoothly varying direction fields. So I will next describe how wavefronts are generated, and without loss of generality, I will show the wavefront aligned with the normal direction, but keep in mind that it's the same for the bitangent one. So wavefronts are generating using a field that we call wave fields, and simply put, wavefronts are the zero-level set of particular scalar fields that we refer as wave fields. And this reformulation is advantageous because wave fields are scalar functions that are relatively easy to optimize for both spacing and field alignment, allowing this objective to be achieved indirectly through smooth continuous field rather than directly on the curve geometry. And I will now better explain how wave fields are generated using state-of-the-art methods. Wave fields are discretized on a regular grid, and for each voxel, we encode a cosine wave described by the following equation. And the equation consists, of course, of several terms. The first is the sine distance from a point x to a plane passing through the voxel center and oriented with a given per vortex direction. And this term defines a plane wave propagating in the specified direction, and most importantly, by varying this direction in each voxel, we can obtain waves that align with a spatially varying direction field. Next, we include a term that controls the frequency of the wave, and we use the value pi over tau, which ensures that the isosurfaces are spaced at the target distance value tau. And lastly, we include a per voxel phase offset term. And this component is important because it allows the wave to be shifted independently in each voxel, providing additional degrees of freedom to align the wave locally across the grid. In the end, constructing a wave field requires specifying the direction and frequency as input parameter. The remaining degrees of freedom are the per voxel phase offset, and these are optimized to produce a coherent scalar field by locally aligning the waves across neighboring voxels, ensuring consistent and smooth transition throughout the domain. So we perform this optimization iteratively, and at each iteration, the phase assigned to a voxel is determined from the phase value of its neighboring voxel in the previous iteration. In practice, aligning a voxel with its neighbor is achieved by first defining the alignment with a single neighboring voxel, as shown on the left, where the central voxel in blue is aligned with different neighbors. The final phase value for the blue voxel is then computed of the average phase of the one prescribed from each of its neighbors. So in the end, performing the wave field optimizations only require to define how to align the wave of two neighboring voxels. So here we assume that the phase of the voxel V is the one being updated, while the phase of the voxel Q is fixed and corresponds to its value from its previous iteration. And before introducing the formula, I want to explain the reasoning behind it. Since it is not possible to fully align waves with different directions over their entire domain, we have to enforce a weaker condition. Cosine waves should have the same value at the midpoint between vertices. Voxel. And this choice of the midpoint is motivated by the fact that when interpolating the wave then of neighboring voxel, we want their value to match at this location. And this choice works reasonably well, as you can see. However, the waves are not perfectly aligned away from the midpoint. And this is a fundamental limitation of the formulation, as the optimizer does not have enough degrees of freedom to align the waves everywhere. To improve quality, we typically use a finer voxel grid relative to the wave period, as it increases the available degrees of freedom for the optimizer. However, in this example, we just prefer to use a coarser grid so we can better visualize the wave in each voxel. There are also some edge cases we want to consider. The first is what happens if you have orthogonal directions. As you can see, the waves do not really align in this case. However, as there is no clear better solution here, there is not much we can do, and we just have to accept it. A much more interesting case is what happened with opposite direction. Here the waves at first seem almost aligned, but if we shift the phase, we can see they move in opposite direction. And this clearly shows how enforcing the same value at the midpoint will not be enough to align waves. However, this is fairly easy to fix, as if we consider it careful, there will be always two phase values that they can produce the same cosine value. And among the two choices, we can select the one that ensures that the wave propagates in a consistent direction as well. And this is essentially why we model all the previous direction fields as to rosy. However, when aligned opposite direction, we can only enforce consistent cosine wave. The underlying phase field become misaligned and produce misaligned sine waves as consequence. Therefore, extra care should be used if one is interested in those fields rather than just the cosine wave itself. So to conclude, this would be the final equation for aligned two neighbors, and I don't want to go into the detail of the derivation. I just want to emphasize that in the end, it's a very simple and efficient closed form formulation. So to accelerate convergence, we also rely on a multi-grid strategy, require only 32 iterations per level, and these iterations are completely parallel, resulting in a really fast solver. But for more details, I will refer you to the paper. Now that we have dealt with the wave field generation, the next step will be to extract the wavefronts. However, each voxel stores a cosine wave, and for isosurface extraction methods such as Marching cube, each voxel should have a single scalar value that is then trilinearly interpolated. We obtain this by simply evaluating for each voxel its wave at the voxel center. Note that as our voxel size is really fine, of tau over 4, is sufficient to avoid aliasing artifact that could be caused by this trilinear interpolation. So to recap, from the frame field, we generate two orthogonal wave fields, and their isosurfaces define the wavefronts. And finally, the intersection of the wavefront produces a set of curves. To enable us to later connect all those curves into a single one, however, it is really, really important that we only obtain closed curves. Nevertheless, trying to intersect meshes robustly is far from trivial. So the next challenge is how to robustly extract those curves. Taking a step back, our curves are implicitly defined as the intersection of zero-level set of two orthogonal scalar fields. At this point, wave fields are just scalar fields stored on a voxel grid and trilinearly interpolated to obtain a continuous representation. So we must extract the intersection of the zero-level set while ensuring that the resulting curves are well-formed and closed without degenerate configurations such as isolated points of valence 0 or ambiguous crossings on valence 4. However, again, directly intersecting arbitrary scalar field will not guarantee this property. To robustly obtain only closed curves, we use a multi-stage approach. First, we extract the isosurfaces of the first field using marching cube. And by enforcing appropriate phase constraint at the boundary of the domain, we ensure that no isosurfaces cross this boundary, which guarantees that only closed surface will be generated. To avoid the degenerate intersection, we also perturb voxel value when the scalar field is too close to 0, and this prevents ambiguous case at the iso value threshold and ensure that a manifold mesh is produced. Then we sample the second field on the extracted isosurface of the first field, resulting in a scalar field that is now defined over a simpler triangular mesh. And finally, we apply marching triangle to the scalar field to extract a set of isolines on the mesh. Again, we perturb vertices whose values are too close to 0 to avoid the degenerate case and ensure a clean, well-defined set of curves. Last, we discuss the stitching step that connects the set of closed curves into a single one. As shown in the work from Kang and Keda, a single continuous curve can be obtained by stitching together a set of closed curves. In practice, closed curves can be joined pairwise to form a single curve by selecting a pair of stitching points on each curve. For example, the purple and yellow curve on the left are joined into a single yellow curve on the right. And this operation can then be iterated until a single continuous curve remains. For the stitching step, the main objective is to promote that the pair stitching segment lies at the correct distance. And to achieve this, we uniformly sample the curve and enforce stitching point to separate it by the distance tau. And among all the possible stitching candidates, we then select the pairing that minimize the length of the newly introduced segments. And these encourage short stitches that preserve the original geometry as much as possible. While we finally obtain a field-aligned volume filling curve, small spacing issues may still remain near wave-field singularity, as highlighted in the red circle. And to address this, we apply 8 iterations of the method proposed by Noma and colleagues. And although this approach does not explicitly support field alignment, the curve is already in a near-optimal configuration, so this iteration primarily improves spacing while introducing only minimal change to the overall alignment. So, with this done, let's look at some results. Starting with qualitative results, here you can see a curve aligned with the direction field composed of two piecewise constant directions for the front and back part of the object. As shown, even in the presence of sudden change in direction, our method produces a high-quality volume filling curve. In this example, the direction field is orthogonal to the nearest boundary, demonstrating that our method does not require a field that conforms with it. Nevertheless, using such a field as shown here can produce much smoother results. Lastly, here we use a field with randomized blue noise direction, and we still obtain something that is a reasonable result. In general, we find that the curved tangent field allows us to control the overall appearance of the curve, which may be of interest in animation and VFX, as shown in this short clip where two curves are being generated from the same solid, but with really different direction field. Again, as qualitative metrics are not sufficient, we also need to define quantitative ones. First, we measure the deviation between the curved tangent and the prescribed direction. And notably, since our fields are too rosy, we must include an absolute value in the metric to account for the sign ambiguity. We also want to measure the curve spacing. To do this, for each point on the curve, we consider the distance to the closest point that is sufficiently far away in terms of arc length, and this effectively filters out nearby points along the same curve segment, and allows us to better capture the concept of distance to neighboring parallel segments. Lastly, to measure the filling error, we quantify how much of the distance of each point in the domain exceeds the target maximum value. With this metric, we can compare our method, shown in orange, with repulsive curve approach, shown in blue. As you can see, our method achieves significantly better alignment and spacing while requiring only a small fraction of the computation time. We computed histogram of these metrics across many objects, As shown, results are overall quite good. In particular, the filling error is generally low, with a few exceptions in small detail region where the curve struggle to fit, such in the ears of the armadillo. Here we have additional example, and what is in particularly interesting is the bunny, where random direction field has been used. And this makes the problem highly challenging, and indeed there is a big deterioration in the deviation metric. We also studied how different spacing and tangent field affect the curve, and to this end we used two different fields, one parallel to the object boundary in orange and one orthogonal to it in blue. And we computed aggregated normalized metric for decreasing spacing values, and as shown, reducing the spacing provides more degrees of freedom to the optimizer, allowing to achieve better results. And going into more performance detail, we can see that our method is overall quite fast. However, due to the volumetric nature of the problem, reducing the spacing greatly increases both runtime and memory consumption. The effect of the direction field is also quite noticeable, as the blue case requires many more stitches, which is the most expensive part of the pipeline. In the end, the large examples shown here contain more than 10 million vertices and took over 5 hours on a desktop CPU and nearly 30 GB of RAM to compute. Nevertheless, the results show a massive volume filling curve with tangent alignment with the normal of the nearest boundary of the solid. Notably, this tangent field generates several sudden changes of direction at the medial axis. We also conducted an ablation study of the necessity of the repulsion as a post-processing, and as shown, while the histogram remained largely unchanged, the spacing near singularity is greatly improved. We also tried other strategies to construct the frame field. Here we show the result using the smoothest normal for the frame field I described earlier. And starting from a tangent field in the horizontal direction, here the smoothest field results in a vertical one, producing the wavefront shown on the left. And here we show a frame field where the normal is orthogonal to the object boundary. As you can see, the choice of normal has a great impact on the wavefront, which also propagates to the final curve. And here are the two results side by side. And as you can see, while orthogonal normals field produce better, curves that better follow the object boundary, the impact of the quiet matrix is quite significant. Lastly, to ensure the robustness of our pipeline, we run in more than 4,000 solid models with a single connected component from the Thingy10K dataset. And in the supplemental material, we provide the 3D rendering for all the results. So a few final words on the limitations of our method. First, it should be noted that in the robustness experiment, our algorithm will fail to fully fill the volume of solid with really fine geometric details. And in such case, the stitches may also then extend outside of the solid that they are here shown in red. In future work, it might be possible to use geodesic path for the stitching to address this limitation, but at big cost of performances. Additionally, the spacing with respect to the boundary, which should be approximately tau-half according to our objective, is consistently larger in our experiment. And improving this spacing between the curve and the object boundary may be of great interest for fabrication application, but is left for future work. To conclude, here you can find the link to the source code that is available, and thank you.
Thank you for the nice talk. Any questions?
Thank you. The results look really cool. So you talked a little bit about requirements on boundary conditions of the field, but do you have any thoughts on what field energies would best promote, the kind of results you need for this method?
Oh, the boundary is hard constraint. As we are doing an iterative optimization, and every time we change some phase value, if the one constraint are fixed, they will never be updated. So this enforces strong constraint at the boundary. And we know how the phase propagates from the boundary, so we know which phase we should set there so it propagates at the right distance on the interior. So they are really simple constraints to set. And if you have a multigrid, then they will converge really fast.
But I mean, if you were designing an optimization method for fields specifically for use in this kind of method, would you choose a different optimization objective than you would for use in some other kind of application?
Well, I mean, depends on your application. You may want to change things like spacing, direction, and things like this. They may be considered objective. But overall, I would say this is pretty flexible. And the boundary constraints really depend how much you want the curve to be far from the boundary, usually, or your geometry. It may also depend if you are extracting things like isosurfaces or crest. Then, of course, you may want to tweak this, but overall, it's always the same as far as I know. But I don't know if you have some specific application in mind.
Okay, thank you.
Thanks. Any more questions?
Great presentation, thanks. I had a small question, maybe you mentioned it, but I missed it. Why do you extract Marching Cube and not have like local rules to try to extract the curve directly from the grid?
So you're asking while I'm doing multi-stage and doing directly, basically.
So you have your periodic field,
yes.
You compute a Marching Cube of this field, then you take the surface on that, then extract it again, and why not have like local rules inside the cubes to try to extract the curves directly?
Because, I mean, you can do this. There are some algorithms like Marching Line that try to do this. The main thing is that the complexity becomes quite exponential because those algorithms are basically big lookup tables. And if you start to have two fields, the size of the lookup table kind of explode. And they are quite tricky to get. Like even the original Marching Cube algorithm, for example, the lookup table doesn't work. It's not consistent. It will have cracks. So it's not so easy to debug. And doing this two-stage approach simplifies a lot because you can always verify that one thing is correct. And then it's much easier to implement because you can find a lot of already existing implementation of this. So it was more listed dictated by practicability, but it's totally possible. You may gain some performance and memory gain by doing this, yes.
Okay, thanks.
Okay, so let's thank the speaker again.